So in the final section, what I want to do is talk about robust systems, how the Erlang approach to building robust systems, and then in particular how to take the server that we built in the last section and make that rather more robust. You can imagine from what I was talking about when I talked about error propagation, it seems that errors propagate right the way through a system in perhaps propagate transitively through a system in a rather uncontrolled way, and potentially at least. And I think the advice that an Erlang architect would give you is to say, make sure that your system is layered appropriately. So numbering layers from 1, increasing the number as we go down the system. That things at level n plus 1 are monitored, supervised by things at level n. So exit messages might be trapped and handled at level n minus 1 if things are going wrong at level n. With the application layer, the work being done at the bottom layer, whatever that is. And again, and this is supported by some of the Erlang libraries and design patterns, application programmers should not have to worry about the error handling code. This code should be isolated in higher levels of the system. So application programmers deal with the normal case, with the unexceptional case, and exceptional cases are dealt with uniformly across the system by the higher level architectural layers. And in fact, we will find that there are processes whose only task is to supervise their children, and these are called supervisor processes. So typically what we should expect to see is a model rather like this, so a clearly layered tree structure in which the top level nodes, which you can see here, are drawn with double circles, meaning that they are trapping exits. These are the ones that monitor the applications that sit at the lowest level. And you can see here we have actually layered supervision here. So the node right at the top is responsible for supervising the lower level supervisors. So we have a huge management structure and then all the work done right at the bottom. In the middle layer, the process on the left is responsible for the first 3 applications, the process on the right for the last 2. And they will model those, and then if they happen to fail, the system at the top will take over and deal with that sort of problem. Now let's go back to our server. We can see that there are problems in that naive server which were brought on by clients coming and going. A client's been allocated a frequency. What if that client crashes before it is able to release the resource? What will happen is that we'll have a resource that's forever allocated, never deallocated. And so we're gradually, if we run with that system, we're going to find that we're gradually having resources used up, and in the end we become starved of resource. So what we want to do is rewrite it in a way that makes sure that if a client does crash, then we will handle that. And in particular, what we'll do if a client crashes is that we will deallocate the frequency that they have allocated to them. So let's have a look at about how that is done. And what we've done is we've highlighted in red the code that is different from that server. And what we have done is say that when we initialize, we put the trap exit flag on to true. So that means that our server process is trapping exits in any process to which it is linked. Now, the next question is, how is it linked to other processes? How is that achieved? Now, what we can see is in the allocate process, when we allocate a frequency to a process with a PID, we link to that PID. So every time we perform an allocation, we link to a process so that our server will be linked to everything which has a resource. And then when we deallocate, we are able to unlink from that PID. So this handles, we have to modify allocation to link, deallocation to unlink, so that during the period that that resource is allocated to a PID, we are linked to that client. Now, what happens if a client terminates abnormally during while the server is still alive and while it has a resource allocated to it? Well, we have linked to it, so now if it does terminate, we will receive a message in our main loop. So what we need to do is ensure that our main loop is extended to handle those new messages that will come in. And what we do here is that we process this incoming message by defining a new function called exited. And what that will do is deal with the situation that we've had. So we see coming in, we match on the atom capital exit with a PID and a reason. And what we do is we pass that PID together with the data structure representing which frequencies are allocated and which not to the exited function. And the final bit of the jigsaw is to see how we deal with that situation. What we do in the exited function is we look up on the PID to see what frequency is allocated to it. And if a frequency is allocated, we deallocate that frequency using key delete. Otherwise, we don't need to do anything. So what we're able to do here is, knowing the PID, we can find the frequency allocated and deallocate it. And so that has the effect, if we go back to the main loop, of showing that when we get that exit message saying that process has terminated abnormally, we make sure that its frequency, looking it up with the PID, gets deallocated, and so that the new frequencies data on which we loop has that frequency free again. And just backtracking one more slide, the way that we're only linked to processes which carry a resource. So we link to a process when we allocate it, we correspondingly unlink when we perform a deallocation. And the final bit of the jigsaw, running backwards, is that when we set up our server process, we set the trap exit flag to true so that we receive these abnormal termination messages as exit messages rather than killing the server. So we're able now to link and unlink, and that the cause of that is for us to receive exit messages from linked processes which terminate abnormally, and what we do there is look up on the PID and allocate. Make sure that that frequency which was allocated to the PID gets recycled. So here we can see another message sequence chart. If we get this final crash, then what that will do is send an exit message to the server. So what we've seen in this example is that robust systems are built by making sure that higher level processes monitor, supervise lower level processes. We'll see that later on when we look at the OTP library and design patterns. And we've seen a particular way of robustifying our server so that it's resistant to clients crashing, and it's also able to recycle resources that are not, so that they're not hogged forever by a client having crashed while being in possession of that resource. And the mechanism we used for that was the linking process, which we talked about in the first section, and linking allows exit signals to be sent between processes, propagated or not according to whether or not we're trapping exits, and As we saw here, when we do trap exits and control whether we're linked, we're able to respond to abnormal termination in a way that makes our system efficient and robust.